All right, welcome back, everyone, for another deep dive. When we use our computers, especially for really demanding stuff like, those crazy detailed video games, it's amazing how quickly everything happens on screen. I mean, there's so much data flying around, but it just works. So today, we're going to delve into how our CPUs, those processors that are like the brains of our computers, manage to handle all that information so efficiently.
Yeah, it's pretty mind-boggling when you think about it. All those intricate details in a game world, all those characters moving around, interacting, the environment changing, and it all feels so seamless.
Right. It's like there's got to be some secret sauce, right? And a big part of that secret sauce is something called the CPU cache. That's what we're going to unpack today. We actually found this super interesting video that breaks it down, so we're going to use that as our guide.
Perfect. And, I think the video starts off with this great analogy using, well, video games, which is fitting.
Yeah, it talks about how early games were often built using what they call object-oriented design. So each thing in the game, like a character or an object, had all its data bundled together, like its position, its health, its appearance, all neatly packaged.
Yeah, makes sense, right? Keep everything related in one place. But as the video points out, this approach actually created a bit of a performance bottleneck.
A bottleneck. How so?
Well, even though each object's data was nicely organized, those bundles for different objects weren't necessarily stored close to each other in the computer's main memory.
Ah, I see. So it's like having all the ingredients for a recipe, but they're scattered all over the kitchen.
Exactly. And when the game needed to update, say, the positions of all the characters at once, the CPU had to jump around in main memory, grabbing bits of data from all over the place. That constant back and forth takes a lot of time because accessing main memory is much slower compared to the CPU's processing speed.
It's like having to run across a huge field every time you need to fetch something instead of having everything you need right at your workbench.
Exactly. And that's where data-oriented design comes in, which is what the video explains next. It's a more efficient approach that flips the idea on its head. Instead of grouping all the types of data for one object together, it groups similar data for all objects into contiguous blocks in memory.
So instead of having all of character A's data in one spot, then all of character B's data somewhere else, we now have all the positions for every character in one block, then all the health values in another, and so on.
Right. And this seemingly simple reorganization makes a huge difference because it plays into the strengths of the CPU cache.
Ah, the CPU cache, our star of the day.
Right. As the video explains, the CPU cache is a small, super-fast memory that sits right next to the CPU. It's basically a temporary storage area for the data that the CPU is most likely to need in the near future.
Like a handy little toolbox, keeping the most frequently used tools right within arm's reach. So how does this all fit together?
The video does a great job of breaking down the process. When the CPU needs a piece of data, it first checks the cache. If it's there, boom, super-fast access. But if it's not, that's what they call a cache miss.
And what happens then? Does it just grind to a halt?
Not at all. When there's a cache miss, the CPU has to go fetch the data from main memory, which is slower. But here's the clever part. It doesn't just grab that one specific piece of data. It grabs a whole chunk of data, a cache line, that includes the data it needs and also some of the data that's stored right next to it in main memory.
Ah, so it's like grabbing a whole stack of papers, even though you only need the top one, assuming you'll probably need the others soon, too.
Exactly. It's a preloading strategy based on the assumption that if you're accessing one piece of data, you're likely to need its neighbors soon as well. And this is where data-oriented design really shines. Because now, if the game needs to update the position of another character, and those positions are all stored next to each other, there's a high chance that the data is already in the cache from the previous fetch.
So that would be a cache hit, right?
Bingo. And a cache hit means the CPU can update that position directly within the superfast cache without having to go all the way back to main memory. This is how data-oriented design and CPU cache work hand in hand to significantly speed up processing.
It's all about minimizing those slow trips to main memory. Fascinating.
And, there's a fundamental principle at play here that the video explains, the principle of locality of reference. It has two parts, temporal locality and spatial locality.
Okay, so temporal, that sounds like time-related.
Precisely. Temporal locality means that if you've accessed a piece of data recently, you're likely to need it again soon. Like in our game example, a character's position is constantly being updated. So keeping that position data in the cache makes perfect sense because it's going to be accessed repeatedly.
Makes sense. And spatial locality.
Spatial locality means that if you access a memory location, you're also likely to access nearby locations soon. Our data-oriented design takes full advantage of this. By grouping similar data together, we increase the chances that when one piece of data is fetched from main memory, its neighbors will also be fetched, leading to more cache hits and faster processing.
It's all about smart organization, both in how the data is structured and how the cache is designed.
Right. And speaking of cache design, the video then goes a bit deeper into how the cache itself is organized. It focuses on the data cache, which is what we've been talking about, the part that stores the actual data. There's also something called the instruction cache, which handles the CPU's instructions, but we'll stick to the data cache for now.
Sounds good. So how is this data cache organized?
Well, the basic unit of the data cache is the cache line, which is the smallest block of data transferred between main memory and the cache. They're typically around 32, 64, or 128 bytes in size.
Okay, so the data comes in these chunks, but how does the CPU know which chunk holds the specific data it needs?
Each cache line have a tag, which acts like a label. It identifies where that chunk originally came from in main memory. So when the CPU is looking for data, it can compare the address it has with the tags in the cache to see if the right data is present.
Like a postal code on a package, making sure it goes to the right destination.
Perfect analogy. Now, the cache isn't just one big pool of these cache lines. It's further divided into sets, and each set contains a number of cache lines called ways. This is called an n-way set associative cache.
So N is just the number of ways in each set.
Exactly. The video used an example of an 8-way set associative cache, meaning each set has 8 cache lines. Think of it like a cabinet with drawers. Each drawer is a set, and each compartment within a drawer is a way.
Makes sense. So how does all this mapping work? How does the CPU know where to put data in the cache and then find it again later?
The video uses a great example to illustrate this. Imagine a computer with 64 gigabytes of RAM and a 32 KB cache. A 64 gigabyte address needs 36 bits to represent it, so when the CPU wants to store data in the cache, it splits that 36-bit address into 3 parts.
3 parts.
Yeah. First, there's a 24-bit tag that identifies a large chunk of main memory. Then there's a 6-bit set index that tells the cache which set to use. And lastly, there's a 6-bit offset that pinpoints the exact byte within the 64-byte cache line.
Okay, I think I'm following. So when data needs to be stored, the CPU sends the data along with the full 6-bit address. The cache uses the set index to pick the right set, stores the data in an available way within that set, and also stores the tag for later identification.
Exactly. And when the CPU needs to read data, it sends the 36-bit address again. The cache then uses the set index to find the correct set and compares the tag from the address with the tags of all the cache lines in that set. If it finds that cache hit, it uses the offset to grab the exact byte and sends it back to the CPU.
That's really clever. It's like a super efficient lookup system.
It really is. And the video briefly touched on some different cache architectures. There's fully associative cache, where data can go anywhere in the cache, which is flexible but more complex to manage. Then there's direct mapped cache, where each memory location maps to only one spot in the cache, which is fast but can lead to conflicts.
And most real-world CPUs use something in between, right?
Right. They use n-way set associative, which balances flexibility and speed. And lastly, the video mentioned cache replacement algorithms, which decide which old data to evict from the cache when new data needs to be stored. But we won't delve into those today.
Sounds like a topic for another deep dive. So after all this, what's the main takeaway about CPU cache?
Well, the key is that the CPU cache is a crucial piece of the puzzle when it comes to making computers fast and responsive. It leverages those principles of temporal and spatial locality, taking advantage of how programs access data to minimize those slow accesses to main memory. And this is exactly why approaches like data-oriented design are so important, because they help maximize cache efficiency.
It's all about working with the hardware to ensure the software can run as smoothly as possible.
Right. It's a beautiful example of how understanding how things work at a low level can lead to significant performance improvements. And speaking of performance and efficiency, it actually reminds me of our sponsor for today's deep dive, Stonefly. They've been in the data management and protection game for over 2 decades, and they really understand the importance of keeping data accessible and safe.
Oh yeah, that's a great connection. Tell us more about what they do.
Well, as a technical engineer at Stonefly, I can tell you they offer some really robust solutions, especially when it comes to backup and disaster recovery. One of their key products is the DR365V appliance, which provides what they call immutable and air-gapped backups.
Immutable and air-gapped. What do those terms mean?
Immutable backups mean that once data is backed up, it can't be changed or deleted. which is incredibly important for protecting against things like ransomware. And air-gapped backups add another layer of security by keeping the backup data physically or logically separated from the main systems, making it much harder for attackers to get to.
So it's like having a separate vault for your most important data, completely isolated from the main building. That makes a lot of sense in today's world where cyber attacks are becoming more and more common.
Absolutely. And the DR365E is more than just a backup solution. It's a full-fledged DR appliance that supports popular platforms like Veeam, Rubrik, and Commvault. It offers features like site recovery, so you can quickly get back up and running if something happens to your primary systems. And it has object lockdown technology to further strengthen protection against ransomware.
It sounds like they've really thought of everything to keep data safe and accessible.
They really have. Stonefly's been doing this for over 20 years, so they have a deep understanding of what businesses need when it comes to data management. And the DR365V is a great example of that expertise in action.
That's fantastic, and I heard there's a special promotion going on.
Yes, they have a limited time offer on the DR365V. It comes with a base capacity of 70 PBD, which is expandable all the way up to 4 petabytes. That's huge. And it includes all those features we talked about: air-gapped and immutable backups, support for Veeam, Rubrik, and Commvault, site recovery, and object lockdown technology, all for a starting price of $7,995. It's a testament to how seriously they take data protection and how they're making it accessible to businesses of all sizes.
That's a great deal for a comprehensive solution like that. We'll definitely include a link in the show notes so our listeners can check it out.
Great. You know, it's really interesting how those principles of efficiency and data protection that we see at the CPU level with the cache and all also apply at a much larger scale when we're talking about managing and protecting an organization's entire data infrastructure.
Absolutely. It's all about having the right data in the right place at the right time, and that applies whether we're talking about a single CPU or a whole network of servers.
All said.
So we hope this deep dive into CPU cache has given you a better understanding of how your computer works its magic. And maybe it's even sparked some thoughts about how we think about data in our own lives. It's a topic with implications that reach far beyond just our computers.
Definitely. It's something worth pondering.
As always, if you have any questions or topics you'd like us to explore, please let us know. Until next time, stay curious.
See them?
Bye, everyone.